So there we go. Okay, can you guys see up on the screen there?
Yeah.
Yep. All right. So I've obviously done the homework on now the tablet, and we can have a look at what was going on. I'll highlight as we go through what I was doing. And if you have any questions or you're unsure about anything, just stop me and I'll try and explain in a little bit detail. Yeah, I've also drawn a graph for you guys just to explain. We're kind of going to get into it in the next topic, but just to explain to you why you would have got some negative values. All right. So if we have a look at the first one, it was very basic. It just asked for the integral from 1 to 2 of 3x squared, right? Now, we could have gone and drawn the graph of 3x squared and tried to calculate the area under the graph, but obviously it's a curved graph and you know that that's going to be very difficult. So the easiest, we've learned this new technique where if we use some calculus, we can take the primitive function. And so that's the first thing that I've done here in blue, is I have anti-differentiated the function, right? And then I've just simplified it into x cubed, right? And we mustn't forget these guys over here, right? Because that tells me this is a definite integral. If I leave those guys out, then I've got an indefinite integral. And if I have an indefinite integral, then I must remember to put in Charlie, okay? So the only reason we don't have plus c here is because they're basically going to cancel each other out when we do the next step, okay? So in the next step, we basically say, okay, we take this primitive function and we're going to take the end value and we're going to subtract the starting value, all right? And from there, all we do is everywhere we have an x, we are going to substitute x in like you've always been doing and work out the solution, okay? So you're starting at 2, you're going to substitute 2 in, and then you're going to take away 1. And that would have given you a value of 7. Okay? So let's move on to the next one. Okay, the next one wasn't really difficult, but I've gone into a bit of detail just to give you an idea of where we're headed today. Okay, so we're looking at this another integral, in other words, an area under a graph, and this graph happens to be the graph of 2x minus 3. Okay, now actually what we could have done is we could have drawn the graph of 2x minus 3, and we could have worked the area. As you can see, I've actually drawn the graph over there for you, and you can see I've worked the area out under the graph, okay? And we're going to discuss this later on, that when you get asked to find these integrals, right, or these areas, you don't have to get the primitive function. If it's a straight line or something that you can work it out with, then that's what we're going to do, because it is actually easier. Right? Taking integrals or finding primitive functions requires a lot of work and it's error prone, and so we actually try to avoid it, right? But anyways, you wouldn't have known that, so you would have found, for me, you would have anti-differentiated your function to get the primitive function, right, which is over here, and I've just simplified it into something nice over there. And again, we are looking at this thing from these two limits. We call those guys limits, okay? And obviously, once you plug these numbers in, you would have noticed that you got a negative area, all right, a negative amount. And if you have a look at the graph, have a look at where the area is, okay? You can see that it's basically below the x-axis, all right? And because if you think about these areas are basically the y-coordinates multiplied by that tiny little width, right? That tiny little dx, that change, right? And because the y values of your gradient function are negative, you're obviously going to get negative gradient, okay? And we're going to discuss this in detail, why and how this gets used, and why we have to be careful sometimes when we're working out area. We're going to have to be very careful about what the question asks us, okay? So just to give you an idea, right? When we talk about area in calculus, right, the integral gives us what we call signed area. In other words, it takes the area for its value. Either it's negative or it's positive, right? We know that area actually isn't negative, right? You don't get such a thing as negative area. Area is always positive, right? And the way we're going to think about this area in the future is Well, it depends what the question is asking us, right? So to give you the most basic idea, if you can imagine yourself looking at this graph and thinking this is a velocity graph, for those first few seconds or minutes, this person was just having a negative velocity. In other words, they were going backwards, okay? And obviously as the velocity increased, they were going forward. So it was a change in direction, okay? So we'll discuss that a bit more in detail when we look at area under the curve just now. Right, I'm going to move on. All right, I'm going to skip E, and I'm just going to move on to one of the more trickier ones. So here we have 2B, right? So the first thing you look at when you look at these guys is you have a look and you see, I don't know how to do anything with a function like that yet. So obviously I need to either simplify it or turn it into something that I can work with. And that's exactly what I've done over here. Right? I've just split the two terms by the denominator, and then I've brought that x squared up to the top. Right? So from here, I can now find the primitive function. Because I can't draw this graph, I don't know what it looks like. So the only way I can find the area is to find the primitive function. So here's my primitive function over here. And again, I've just simplified it, and don't forget that it is between those limits. Okay. Now, it does seem strange to put a big number in second, but remember this is -2 and -1. So just keep an eye on which values you plug in first. This is the end, and this is the start. So we put our end values are all these -1s, and my start value is all these -2s. That would have given you an answer of 3. Again, guys, shout if you are not following or understanding, and I will slow down. Right, question D. We had, again, just a function that we had to expand out because we don't know how to differentiate or anti-differentiate a function that is two products yet. So we had to expand the brackets out, and we had to change the square root sign into indices notation. So I've just changed this square root x. I've multiplied by 1 to get square root x, and I've changed it into...
Wait, how did you multiply? How did you multiply out the brackets?
Okay, so what I did is I just took the square root of x times by 1, yeah, which gave me the square root of x, because anything times 1 is just the square root of, well, is it the same as what it is. And I've just immediately converted into the power of a half, because I can't work with the square root of x. I need to change it into index notation. Okay. Then for this minus x, what I've done is, if you think about it, the square root of x is just x to the half. Okay. And when you multiply two things that have the same base, we add the exponents. So I've got x to the half plus 1. So 1 plus a half is just 3/2. So that's where I've taken this x square root x times this minus x gives me still minus x to the 3/2. Okay, this 3/2 is just x to the half from that square root times by x to the power of 1. So I've got basically a half plus 1, which gives me 3/2. Does that make sense to her?
Yeah.
Okay.
That makes sense.
Cool. Okay, from there we just had to do it. You can see it gets pretty yucky. All right, so you have to just be very careful. Okay. So we are first, remember, we're finding the primitive, so we are raising the power first by 1. So a half plus 1 is 3/2, and then we're dividing by the new power. And we're doing that again for the second part. We are raising the power, so 1.5 plus 1 is 2.5, which is just 5/2. And then I'm dividing by that new power. Okay? And then don't forget your limits. So like I said, it can get pretty messy. So that's why I've cleaned everything up on the other side. And now I'm ready to find the area. So I'm going to take my primitive at my upper bound, which is 1, take away the lower bound, which is 0. And after crunching the numbers, I get 4/50. So you can see this is where the days of showing you're working out, doing things line for line really comes into play, right? Because these things get very messy very, very quickly. Okay, I'm going to move on to question 5. Now, if you tried it, I hope one of the guys shared the links for you for the videos that I posted yesterday. Otherwise, I can also just link it on the Edmodo page. Okay. I did do.
I think Son sent on the group. I'm not sure. I'll check.
I
sent it to you.
Thank you very much.
Oh,
anyway,
yeah.
So I have made a video going over these questions. So I did question 4 in a little video for you. So if you're still struggling, right, you can go have a look at the video. I went into a little bit of detail on how this works, but I'll quickly go through number 5 just so that we can move on. So if we have a look at this function, the first thing they're doing, they're not asking anything tricky. All they're saying is differentiate this function. That's all. Okay, and we can do that in our sleep, right? There's nothing funny. There's nothing under the denominator. There's no square roots. This is a very nice, simple compound function. Okay, function in a function. So we can just use the chain rule, right? And you can see here I have differentiated the outside. All right, so I've dropped this power down to the front, and then I've reduced the power by 1. And then I need to differentiate the inside, and the inside is this x cubed. And if you differentiate x cubed, you drop the power down to the front and reduce the power by 1. That gives me 3x squared. And I've just tidied everything up over here just to make my life nice and easy. Okay, because I'm going to be comparing this thing in a second, right? This is where we're comparing two gradient functions, right? And we're seeing what their primitive functions might look like. Okay, so the next part of the question asks me, right, find the integral. In other words, find the area under the graph of this guy over here. Right, now if we look at the inside of that function, you can see we have an x cubed, right? And we've learned now we can't really anti-differentiate a function like that unless we have something to compare it with. But that's exactly what they did in question 1. They gave you some function to compare this with. So we put them right next to each other. We make them equal to each other, right? So I've taken my x squared that I've been asked to work, and I'm comparing it to the result of what I got from part A. And I can see that this function that I got in part A, right, is 15 times bigger than what I'm being asked to solve. In other words, if I wanted to make them equal, I would have to multiply the previous one that I've solved by 1/15. Or if you're more comfortable today, you can divide by 15. That's entirely up to you. Okay, it's the same thing. Okay, so that means if the result from the previous one is 15 times greater, right, then its primitive, or sorry, its gradient function is 15 times. Sorry, actually, its primitive is 15 times bigger. And so if I want to use that, I'm going to have to make it 15 times smaller in order to get the desired result, right? And so that's why I have, it's 1/15 of my original function. So there's my original function over here. And what I'm comparing to is 1/15 of that. Again, if we didn't have these limits over here, you would have to actually add Charlie in there, but we've got these limits, and so we can actually evaluate them, and Charlie would just cancel out. And after crunching all the numbers, we end up with this 2 and 1/15. Okay. Right, I'm not going to do the next one. These notes are already up on Edmodo, so if you want to check your homework and see what I did, you're more than welcome to go and do that. And like I said, I've made that little video in any case, so you can go and have a look if you're still stuck. Okay, everybody happy with that so far?
Yes, thanks, Mr. James.
Yeah.
Okay, right. Let's move on to today's work. Today is actually going to be a lot of fun. So we're going to be looking at this, okay? The area under a curve. So if you're following along in your textbook, I believe we are on, let me just check. What is the page number here? 253, I believe, is the page number. Okay, I'm going to do things a little bit different to the textbook, right? But the same idea is going to apply. Right, so if you have a look at the graph that I've got here on the screen, okay, if we consider trying to find the area under this graph, okay, you can see we don't have any kind of formula for working out the area under something like this. I mean, we know how to work out the area under a square or a rectangle, a triangle. We know these basic shapes. They have formula. Okay? When we try to work out the area under a curve, you can see that we run into a problem. Okay? There is no formula for that. What we could do is we could estimate, right? Just like when we are trying to work out the gradient, right, of a point, we could use a point really close by in order to estimate what that gradient is. And so what we could do with this curve is we could, instead of trying to work out the area under the curve, we could estimate it by drawing a series of rectangles, because we know how to work out the area of a rectangle, right? And so what we could do is we could just make and divide this curve into lots and lots of little rectangles. Okay? And these guys are going to go out. Right, so you get the idea here. And you can see that if I had to work out the sum of all these rectangles, their height would just be the y value. All right, you can see that the graph here is f of x. Okay, so their height would be f of x, right? And this little width here would just be, well, whatever change in x I want. I could specify what I want. I could make it 1, I could make it 0.5, I could make it 0.2, 0.3, right? Now, what I want you to imagine is I'm basically summing up, right, all these heights, right? This is just height times width, right? I'm just adding up all these rectangles, and I would get something pretty close to the area under the curve, except you can see there's obviously some gaps in this, all right? You can see there's a little gap here and a little gap here and a little gap here, right? But now what I want you to do is I want you to imagine if we could make these rectangles smaller, right? The smaller we make these rectangles, the more space we're going to take up. And if we could make these rectangles so small, infinitely small, right? We could basically estimate the height under this, or the area under this graph, right? And one place I want you to go back to if you're struggling to understand this concept, remember when we did series, right? And we talked about an infinite geometric series, how if we divide that square up over and over and over and over and over again, right? We can't really keep adding up forever, but we can pretty much see that at some point, those areas are going towards a number. And so we said, as this thing approaches infinity, the area was whatever the value was, okay? And we can say the same thing here. We can say that as this little tiny change in x, right, which I can specify, gets really, really small. In other words, as it approaches 0, then this sum will approach the area under the curve, right? And so that's the basis for what we are going to do today, all right? So I'm going to write down you know this formal definition already, right? We've basically been working with it all the time. That the sum of all these little areas, right? So all these, remember this is f of x is just the y value by this tiny change in x, right? Is the area bound by curve, the x-axis, x equal to a, and x equal to b. Right, now I'm going to draw a little graph to explain to you exactly what this means. Okay, so if you want, you can draw along with me. Here we go. Just a small little Cartesian plane, and I'm going to draw a function that looks something like this. And I'm going to call this guy f of x, right? Which means that my axis, I have x, and this will be f of x. Okay? So what this integral tells me is that if I want to find the area under the graph, right? So let's start at A to B. So let's make B over here. The important thing is you can see that this area is bound by the curve, the x equal to a line, the x equal to b line, and the x-axis, right? So it's this area under here that we are talking about, right? And hopefully you can see that this area is bound. In other words, it's controlled by those four things: the x-axis, the x equal to a line, the x equal to b line, and the curve itself, right? But if you think about it, x is just a variable, right? Because we could change this whole thing, all right? What if I changed all the x's into y's, all right? So how would that look? Well, let's just change all the x's into y's and see what happens, okay? So we could say the integral from a to b. We don't have f of x this time, we have f of y, with a tiny change in y this time, right? And this time it's the area bound by the curve. And the y-axis this time, y equal to a and y equal to b, right? So if we compare those two statements, all I've done is I've changed all the x's into y's. Okay, so let's draw this guy and see what that looks like. Okay, this is going to be f of y because now I'm plugging in y values. This will be the y-axis, right? And I'm going to draw a curve that looks something like this, right? Right, we're talking about y equal to a. So y equal to a is a horizontal line. So this could be y equal to a here. And we can have, let's take y equal to b. Oh, sorry, let's move him down a bit. And you can obviously see now this time the area is not bound by the x-axis, but it's bound by the y-axis. Now this might sound pretty trivial, but you'll see later on where this becomes very useful, right? So I don't want you to get boxed in the idea that we can only integrate with respect to x. Remember, x is just a variable, right? We could change x into anything we like, right? But likewise, we can also look at this idea of area, not under the graph in relation to the x-axis, but we can also look at it with respect to the y-axis. Yeah. Now, obviously, you won't have an equation for y equal to something here. You would have an equation for x equal to something, right? because we'd be plugging in y values to get an x value. Right? So this whole idea of finding area under the curve, okay, has to do with the fact that what we're doing is we're actually just adding up rectangles, right? We're adding up lots and lots of rectangles, and we're basically estimating what this area would be as those tiny rectangles become so small, right? As dx approaches 0, right? The rectangles are going to get pretty small, but just think there's going to be a lot more of them, right? And it's the same idea that we had with gradient, right? When we estimated the gradient, we said, well, as h approaches 0, the gradient is approaching this value, okay? It's the same thing with the area. So when we have these area problems, when they ask us to work out these kind of area problems, there are two ways that we can go. The first way is by actually working out the area under the graph. Okay, so if we have a graph where we have a shape under the graph that we can actually work out the area, well, then that's how we work out the area under the graph. Okay, but if we have a curved graph or something that we don't know, well, we learned this new awesome calculus technique that if we take the primitive and we take the primitive at its upper and subtract its lower bounds, it also gives us the area under the graph, right? So whenever we're dealing with these kind of area problems under a curve, we're always going to look at the problem and work out what the most efficient method's going to be, right? Because both of them essentially give us the same idea. Everybody still with me?
Yes.
Okay, right. Let's look at a very important concept in working out these areas. Okay, so we're going to look at the difference between area and signed area. Right, now this is obviously quite an important concept. So I'm going to say, let's consider a nice easy function. This is the gradient function. Let's consider the function 2x minus 4. And I encourage you guys to follow along with me. I'll quickly get through this down. I encourage you to do this problem with me, right? Now, if we think about this function, 2x minus 4, this is a straight line. And if you think about it, you could actually work out the area of this just by working out the areas of the two triangles. But let's consider that we don't know how to do that. So we're going to find the area. We want to find the area under this graph, right? Between 0 and 4. And we're just going to assume that we don't know how to draw this graph, or we can draw it, but we don't know how to work out its area. So we're going to use our other technique of finding the primitive to help us find the area. Okay? So the first thing we need to do is we need to find this primitive function. So we're going to anti-differentiate to do that. Okay? So if I anti-differentiate 2x, right, what will I get, Dominic?
X squared.
Yeah, you should just get nice round x squared. And if I anti-differentiate minus 4, I'm going to get minus 4x. Now, because I am taking this between two limits, I can ignore Charlie. So Charlie will just die in one. So what I'm going to do now is I'm going to take f of 4, and I'm going to take away f of 0. Okay? And let's see what we're going to get. So everywhere we have an x squared, I'm going to put 4. We're going to get 4 squared, take away 4 times 4. That's f of 4. And I'm going to take away 0 minus 0. And I'm going to get 0. And now that's interesting, isn't it? How can you have an area of nothing, right? An area of nothing doesn't exist. Okay, so let's draw the graph of 2x minus 4 between 0 and 4, and let's see what's going on here. Okay. Here we have x, here we have y. So I can see if I have 2x minus 4, that's going to come down here at minus 4. It's going to pass through the x-axis at 2, and it's going to come up here at 2. So I'm going to have a graph something like this. This is 2x minus 4. Okay, there's minus 4 here, positive 4 here, and this is 2. Now, the area I was asked to find is the area bound by the curve and the x-axis, okay? So that means I'm looking at the area from the curve or the line to the x-axis. Now, if I look at the first half from 0 to 2, that happens to be below the x-axis. And if I look at it from 2 to 4, I can see that this area is above the x-axis, okay? And what you saw when we're doing the homework questions is what this integral gives you is signed area, okay? Because the area can be both positive and negative. So that's quite an important thing that we've basically just discovered. We can have positive and negative area. And I'm sure you can work out where that's going to happen. If it's above the x-axis, we're going to have a positive area. If it's below the x-axis, we're going to have a negative area. Now, if you have a look at those two areas, you can see that they are they are exactly the same. The one is negative and the one is positive. And that's why when we added them together, they canceled each other out, okay? So this integral gives us signed area, okay? In other words, it doesn't take into account, or it takes into account that the area is or can be negative and positive at the same time and adds them together, okay? So if I wanted to find the area under the graph, right, I would have to take the unsigned area. In other words, I would have to subtract that negative area because two negatives would make a positive, right? I'd have to add the two areas together, right? Now, I wonder if any of you can think why we would have two different answers, right? If you think about this function, let's assume that this function that we're talking about, 2x minus 4, if you consider that this is a velocity function, right? What's happening?
Started going backwards and then sped up and went
Up
forwards.
forwards, okay? So if I think about this in terms of displacement, right? Because remember, I can work out my displacement from my velocity, right? This just means for the first 2 seconds or 2 minutes or 2 hours, this object was going backwards, right? And then what happened at time 2? Well, the gradient is 0, and we know that the gradient of 0 just means that it's a turning point. Okay? In other words, this person turned around and started going in the opposite direction. So this gives us two very different solutions. Okay, so what we can do is we can very quickly just draw this graph of, well, if we take the primitive function, the primitive function is going to be, in other words, the displacement function is going to be this x squared minus 4x. Okay, so I can very quickly just draw that for you. We have between 0 and 4, right? It starts, it's a happy parabola, so it's going to have an x-intercept of 0 and 4, and it's going to look something like this. This is x squared minus 4x. Okay. Right, if this was the gradient function, this is the primitive function. In other words, this is the displacement function. It tells us how far we are from where we started. Okay, so you can have a look here and see that we started at 0. Then we went backwards. And where did I end up after time 4? Who wants to venture a guess? What's my total displacement? What's my y value? It's 0. In other words, I started and ended in exactly the same place. So what the signed area is giving you is total displacement, right? It's telling you how far are you from where you started. Right? If we cut out, guys, just reload Zoom for the last 5 minutes. So this total displacement, or this signed area, in other words, the way we did it first, it gave us our total displacement. How far away I am after 4 seconds or 4 minutes, right? What is the area going to give us? Kiana, can you take a guess? What if I had to take this from the other point where I worked out the unsigned area, what would the unsigned give me?
Distance?
The distance that I traveled, right? The total distance that I traveled. I didn't travel nothing. I've traveled something. The only thing is the distance that I traveled brought me straight back to where I started. So the unsigned